There is a companion paper to the kilometer scale climate model that looks more specifically at the ocean modeling issues in terms of the resolutions needed and some of the issues that come up when you use lower resolution models based on computational limitations, resource limitations, and so on. So this is the first figure from that paper, which is showing the nice shot of the Southern Ocean here with a model at 2.5 kilometer resolution. So you can see on this corner, and then here you have fine resolution at 8 kilometer, and you have coarse resolution at 25 kilometers and coarsest resolution at 100 kilometer. It turns out that the details matter tremendously because the mixing in the ocean, atmospheric response, heat uptake, carbon uptake, other exchanges with the atmosphere and within the ocean, the flows over slopes and exchanges of water masses, all sorts of details get affected by these small scale processes, and it's basically not a very good idea to exclude them. Of course, it has always been limited by computational requirements and what were available when the models were being developed and being run and coupled and so on. So this is now again looking at the same thing in section, finest at 2.5 kilometers. So you can see the North Brazil current getting into the Caribbean Sea, into the Gulf of Mexico, producing these loop currents coming out between Cuba and Florida. Very nicely structured Gulf Stream here. Separation happens and you get all these meanderings, North Atlantic current and becoming the Norwegian current and so on up here. So all these places where the front is very sharp, it's also now known very well that even though the mean temperatures are very cold, there is an atmospheric response often related to the sharp front, hydrostatic pressure response across temperature gradients, and then resulting atmospheric response, which is very different than the kind of air-sea interaction we think about in warm waters. So the title of this, the caption of this figure is Surface Currents at a Range of Model Resolutions from A to C, representation of the surface currents at different resolutions of the Southern Ocean and the North Atlantic here. Data from ICON 2.5 kilometer coupled simulation from the European Union's NextGEMS project. Lower resolution models are from the coupled model intercomparison project CMIP 6. So a lot of the future projections made with for the assessment report 6 and the older ones are coarse resolution models, and there are issues in using coarse resolution models, especially for key features of the climate system like the Atlantic meridional overturning circulation, sea ice extent and sea ice volumes, general heat transport. Climate of the Europe, for example, depends very much on how well the Gulf Stream is done and how the air-sea exchanges are done over here, which themselves are very much dependent on the resolutions and on resolving these features that are important for all those details. Okay, so what are some of the processes? Some small-scale processes in climatically sensitive regions, cavities under ice shelves, deep convection regions like the North Atlantic and the Southern Ocean, key deep ocean overflows like the Fram Strait, submesoscale eddies carrying warm waters across the Atlantic shelf, or the Agulhas rings carrying Indian Ocean waters into the Atlantic, which we'll look at in the next slide, may only be captured by ocean models at kilometer scale. So all these processes which are critical not only for local air-sea exchanges and local ocean atmospheric processes, but actually they affect the Atlantic meridional overturning circulation, which means not only high temporal scale processes but low frequency modes of the Atlantic meridional overturning circulation and related global responses. Okay, this is the comparison of various models used in CMIP 6. It doesn't matter which versions you use, and this is these are transports in the Atlantic meridional overturning circulation being compared at two sections from where observational estimates were made, so-called rapid time period section at 26 north and Samba, which is at 34 south, which we'll look at in a minute. And you can see that the vertical profiles are similar, and yet the differences in transports are tremendous. They are more than 100% away from each other. Obviously, this means the amount of heat being transported and the northern hemisphere southern hemisphere exchanges, which would affect the location of the intertropical convergence zone, for example, which means it would affect the Walker cell, the Hadley cell, and the entire climate system. And similarly at 34 south, you can see that there is a huge difference between the different models, and this obviously has a dependence on resolution, but also in coarser resolution models there is a large dependence on parameterizations of mixing, or how mixing by the eddies is maybe included in some form, and so on and so forth. The mean surface heights shown here to show again this region that we just mentioned. Here is the Samba section at 34 south. There is the Brazil current, which is a western boundary current in the southern hemisphere that cannot be resolved well unless you have very high resolutions. And you have the East Africa coastal current, Agulhas current, coming down here and becoming the Agulhas return flow, and some of the water then has to feed the upper northward branch of the Atlantic meridional overturning circulation with these Agulhas leakage or Agulhas rings that we talked about. And the amount of heat transported, amount of carbon being taken up by the ocean and put away, sequestered and transported, are all going to depend on how well these are resolved. So there is a lot of low frequency rectification, high frequency features that modify the lower frequency heat storage, carbon storage, heat transport, and so on and so forth. This is another example of an ocean model along with different resolutions, so high resolution and low resolution simulations looking at Antarctic sea ice extent for September 1950 to 2099, and then extending into the future to see how the projections also depend on the resolutions. So this is extent in million square kilometers. This is high resolution 1950 controlled run, and here are the observational estimates for 1979 to 2018. And you can see that the low resolution 1950 control run is way up here compared to the observations, whereas the high resolution control is much closer. And you can see low resolution historical run along with the scenarios produces much higher Arctic sea ice extent in the historic period compared to the high resolution historic run plus scenario. So even the future projections of the Antarctic sea ice extent are quite different by millions of square kilometers, and the rate of decline is very different in the two as well. Antarctic sea ice extent is a complicated problem, as we have talked about elsewhere. Southern Ocean is an open channel. When it warms, it can melt away the shelf ice from below, make them unstable by heaving them, but also can increase the atmospheric water vapor because the warm ocean makes the atmosphere warmer and moisture increases, can increase snowfall in some regions and increase the sea ice extent in some places and decrease it in other places, with all the other complications of the West Antarctic ice sheet instabilities and so on happening with the slope flows and ocean interacting with the shelf ice and so on and so forth. So obviously the resolution in the oceans are just as important as the kilometer scale climate model and the processes in the coupled climate system that we talked about. Historically speaking, starting from the 1980s and what we expect by 2050, if we look at the horizontal grid spacings in kilometer with the various processes here, obviously IPCC reports have relied on coarser resolution models. They have added more and more complications instead of in terms of sea ice, land ice, dynamic vegetation, carbon cycles, and so on. And they have to make long simulations starting with pre-industrial levels going into the future with multiple ensembles, multiple scenarios, and so on. Nonetheless, you can see that the resolutions have tended to increase. So as we go down the scale, resolutions increase. So by 2000 we were having more and more increased resolution scenarios, simulations. The evolution of global ocean model resolution, evolution of global ocean model resolution by publication year. Shown are models from the CMIPS in black circles and high-res-MIP, high resolution model intercomparison projects here in red circles, and prototype sub-mesoscale permitting global simulations of the ocean or the coupled climate system in purple stars. Prototype just means that they have not done long simulations to drive equilibrium solutions, but they have been shown as working and producing realistic simulations. Estimated ranges to resolve processes are shown from observations. So mesoscale and sub-mesoscale ranges reflect latitudinal variations in Coriolis parameter and regional seasonal variations in stratification. Studies of coastal, ice cavity, and boundary layer process simulations. These are the references from the paper. I hope you know what mesoscale, sub-mesoscale mean. Basically, the problem of the climate, atmosphere, ocean adjustments are the battle between gravitational pull, stratification, and rotation. So as you go to higher latitudes and Coriolis increases, the balance happens at smaller and smaller scales. So the Rossby radius of deformation, which represents this adjustment, gets smaller and smaller, and the critical processes of the fronts and eddies and mesoscale and sub-mesoscale eddies begin to happen at smaller and smaller scales, because the Rossby radius, which defines the balance between rotation and stratification and the ocean depth themselves, begin to get smaller. Okay, so we can see that now in 2020 some of the high-res MIP and climate prototype models are getting into mesoscale resolution and ocean prototype models as well. So as we go into the future, we may begin to get into finer resolutions and begin to resolve sub-mesoscales and coastal ice cavity resolving models as well by 2050. So we have to have some strategy to run coarser resolution models, knowing the processes missing and the problems they can create. So there are various strategies like nested grids, parameterizations, and so on, which are used, like here, to accomplish some of the goals that can only be in reality accomplished by very high resolution models, which are not here yet. Okay, so the scales you can see keep getting smaller and smaller. Boundary layer resolving models, you can see here, they begin to get into meters. This is kilometers, so you obviously need to get into kilometer scale modeling to resolve some of those issues. So this goes together with the kilometer scale climate modeling that we talked about in the previous podcast, and just keep that in mind, that with increasing computational resources, with increased process understanding, especially mixing and mixing within the so-called surface mix layer, where typically we only used to think about turbulent kinetic energy balancing in the vertical in a one-dimensional sense, but now we know much more about how horizontal gradients in density, etc., can create mixing within the surface mix layer, and so on. So lots of nice work there that you can look up on how those mixing processes are being represented better and better. There are some details still. For example, the separation of boundary currents like the Gulf Stream. It's not always clear that just by increasing resolution everything does get better, but as we increase resolution and learn what doesn't get better, we obviously will learn how to make them better as well, or understand what the missing processes are. Okay, so let me leave it here.